Well, hello everyone. So we finished talking about first order equations, and I see that I made a typo because I'm saying that today we're going to talk about linear first order equations. No, that's wrong, right? So what is it that we're going to do to talk about today? We're going to talk about second second order differential equations. Okay. Um, no, I shouldn't have done that. Go back. Okay. Can I go out in that? So it's second order equations. So I remind you that the second order equation in principle can get already kind of a bit ugly. It depends on x, on y, and on the first derivative. So the second derivative is in terms of these previous derivatives, if you want, and the variable x. That's the general form. And that is actually a very difficult problem to solve these things. And even the ones that we will specify to will be still difficult. We will not always be able to solve everything as we would like to. Luckily, well, one thing, you've seen that these second order differential equations, they appear naturally once you do mechanics, because the Newton's law of motion involves the second derivative. And we mentioned that there is in general a second order differential equation. We were able in the previous session to get a way around it by somehow transforming it into a first order equation, and then we knew we had our techniques. But in general, that might not work. So we have to really look at this class of differential differential equations called second order equations. I haven't said what linear is yet. Second order. And they seem, it's kind of a bit surprising, but most things in nature or in sciences are governed by these differential equations of second order. There are very few cases where we have a higher order differential equation that describes the situation, but it's mostly second order. And luckily, most of this will be of the form that I will now focus on, and this is what this linear means. Okay, so before I say what linear means, well, before to talk about the second order, remember that a first order linear equation looks something like this. Remember that? Linear, because the linear here applies to the occurrence of y. Namely, it appears here as a linear only to the power 1. Okay? Now, we have this is not the only ones we look. For instance, Bernoullis were not linear ones. So there were a few that we were able, and also when we did separation of variables and exact. So this was not the only ones that we studied, but these were the ones that we could deal with the best in some sense. In principle, we can solve this. Well, okay. So what would therefore a second order linear be? Well, linear will now, so if this is for first order, right, let me write it down, this is first order. What does second order linear mean? Now we're talking about the occurrence of y, again as linear, but also of y prime. So it should be linear both in y and in y prime. Meaning what? I mean, I'm just trying to explain where the name comes from, but then perhaps it makes easier to remember what it looks like. Well, y double prime, and remember where this is the general form we solve for y double prime. The same for if the first order would always put something like that, right? That's how a first order would look like. This is how a second order looks like. But very often we split it. Especially with linear ones, we write the linear part here and the constant part here. We do this the same here. So now it has to be linear in y prime. So y prime can only have, let me see that I use the same letters here, sorry. Yes. Y prime can only be to the power 1 here. And that's it. There can be no other y prime. And the same for x, for y. So another qx here. And then what else can there be? Well, there can be nothing in y more, nothing in y prime, so the only thing left has to be, again, an f of x. So you see how very similar the forms are, but of course we have now, instead of a single px here, we have a px and a qx. Okay, that's the one thing. Now, in general, of course, what is, remember, the initial conditions? Let me write that here. Let me get me rid of this one now. Okay, that I give myself a little bit of space. So, initial conditions. If we have a first order, then the initial condition is just requiring that at some point x0, the y value is y0. Another way of saying that is that the curve goes to the point x0, y0. If you would plot it in our direction field, then the y is a curve that goes through this point. Okay, but what in a second order differential equation? Well, that condition is going to be still the same. We're going to always want this, but we need a second condition. We'll see that second order means there are two unknowns. Think of the free-falling object that you saw in calculus 1. That was a simple differential equation, y double prime equals g, right, or minus g, the gravitational constant. If you derive this, you would have to derive twice. So you have two integration constants. And how to determine them? Well, that was, remember, if you look back at it, and we kind of mentioned it already, and I hope you saw it also in the textbook, that you have the initial position and the initial velocity. But remember, what is velocity? That is y prime. So that is exactly what happens in general. What do they say here? Okay. Oh, all right. So I'm going to follow the textbook a little bit so that you don't get too. They use a letter k here to denote these constants. So remember, these are constants, right? Your values. So we in other words, what is the initial condition for the second order is saying what is the position. That is, this is the position, right? If you think of y as a position, sorry, y of course in general could be something else. It could be population or something like that. But if you think of it as a position, as something describing a motion, a mechanical system, then this would be the position and this would be its velocity, for instance. And more generally, this is the original. Well, x0 often is 0, right? But it depends a little bit on the situation. What's the initial? When we say initial condition, we think of something that starts and then goes on, right? These differential equations are always very often about dynamical processes, and then the variable is t, and we very often think as that the t to be 0. But initial condition, you don't take the word initial too literally. It just means that you have these two conditions. One on the y and one on the derivative of y. We'll see what the implications of that are. We'll do concrete examples of that. Okay, now we had also discussed homogeneous, right? So remember, let me write now, if you had homogeneous, if I add the term homogeneous here, what happens? What is the difference? Well, homogeneous means that this was 0. What will homogeneous mean here? Exactly the same thing, that is 0. Okay? And if it's not the case, then we are in the case of a non-homogeneous. So we have the homogeneous one, that's 5.1. Notice that I'm going to do this in a slightly different order than the way it's listed in the textbook. It makes more sense, I think, to do it this way. And then the non-homogeneous one. That would be where we have an actual f. So, so the green is where homogeneous, where we have no f, the f's are 0, and the black is where there is an f. And this is often called... this f is called the forcing function. We didn't call it that for first order, although you can call it there also first order. The reason that we call it forcing function because often when we think of mechanical systems, this is a function that kind of forces it's a function that comes from forcing the movement. For instance, like an engine that propels it, or resistance or something that no, resistance was not a forcing function. But okay, let's not go into the terminology here. This is just makes it sometimes easier to talk about it. Okay, so far where are we? We have let me make sure that my not run out of juice here because it says 100%, and if you look 5 minutes later, it says 60%. So, okay, so, right. So what about solutions? I'm going to go over this extremely waving my hands and just say a few things about it. I'm going to say basically yes. If you have an initial condition and you have an equation like that, you're going to be able to find a solution. At least, well, there's some conditions, like P and Q have to be continuous. What does that mean? It just means a function that we have, whatever functions that we have are continuous functions. So for us, that's not really saying much, or even differential. The P and Q should be differential or continuous, whatever. So for us, whatever function that we will encounter that will work for it, at least perhaps at the very end we will say something about this. But for now, this is not really something we could concern ourselves about. There's one caveat, there's one problem which we have already seen in first order, is that the solution might involve denominators, and therefore the function might not be defined. The particular function that we are looking for might be not defined at certain points. What this means is therefore that you have solutions that are on intervals, defined on an interval where the functions are behaved nicely and don't create poles. Sorry, don't have vertical asymptotes. That's the same thing, but you probably don't know that word pole. So let's not spend too much time on why is this and what the general statements of here. Let's start with an example, and so I'm going to start as I said with 5.1, with the homogeneous one. So here's almost the simplest one you can think of: y double prime minus y equals 0. So let's convince ourselves that this is a first order. Sorry, second order. Well, yes, it's linear also. There is no y prime involved. So if in this case, if you would have to say this, whether if you would say this, so this p here would be therefore 0, and this q would be just constant 1. In general, it might depend on x. In this case, it doesn't. And we see that the forcing function f of x is also 0 here. So yes, so this is what we are dealing with. Sorry, let me give me a sec here. Yeah. Okay, so how do we solve this? Well, that's not so immediately clear how to do that. Okay, so I'm going to kind of cheat and tell you, well, here is the solution, and we will explain later why this, but not. So I'm going to tell you what the solution is, but not how you get it. Okay, so solution, and there will be more. So here is a solution, and I'm going to, okay, here's one solution: e to the ex. Kind of not surprising. Once I say it, you say, oh yeah, of course. Oh, why didn't I think of it? Because you take derivatives of ex, nothing changes, right? So in fact, ex is already and it already satisfies this differential equation, right? But okay, it's satisfied. That can be, right? A function can define different differential equations. Be careful. That's not the differential equation. Does not the differential equation is solution, but the solution don't determine necessarily the differential equation. Okay, so but. Fine, so this is a solution. Okay, now I could ask you for more solutions, and you might come up with, you would first perhaps say, okay, I want to find another one plus c. But then very quickly you realize plus c doesn't work. Why not? Because the plus c here, then, okay, if I take the double derivative, that is just ex, but here it would now be ex minus c. So that doesn't work. But if you think about it a little bit in the linear case, what was it? It was not plus c, it was c times ex, right? If you think about it, where it comes from, just realize where it comes from. If you solve y prime minus y equals 0, that is that is y prime over y is 0. That means the ln of y, if you derive this, is 0, is 0 plus a constant. So we're deriving this, right? If I derive this, or if you want dy here, then we get ln y is 0 times a constant. Sorry. Sorry. What am I saying? Sorry. Let me do this. Okay. I want to do quick, and then quick that never works. So let's do it. Let's take our time. Let's look first what happens in this equation. Okay, so we have to separate the variables. So this is dy over y equals dx. Of course, there is a dx at this side. For some reason, I was blanking out. I was thinking of something else. Okay, so we do this. We enter derive. This is ln y equals, the derivative is x plus a constant d. Then we take the exponential of both sides. So that would give me y equals ex plus d. And that is then ed times ex. So that is c times ex. Okay, that's how we solve that. And so we see that cex is a solution. Any multiple of ex is a solution. Are these the only ones? No, I'm going to give you another one. That one, once you see it, you say, oh yeah, of course, yeah, right. Because if you do it once, you get a negative sign because of the chain rule. But if you do it twice, the signs cancel each other out. Okay? Notice that this guy is no longer a solution of this one, right? It would be a solution if you have a plus sign here. But, okay. Good, fine. Okay, but then professor, I can write you, give any c here will also give you a new one, right? If I multiply this with any c. For the same reason, if you now think of it, yes, of course, it had to be times a constant. Okay, fine. Now I'm going to tell you this one. What about these two guys? If I add them, and I take different C1s perhaps, the constants don't need to be the same, that's why I have a C1 and a C2. They could be the same, but they don't have to. What about this? Think about this. Is this going to be a solution? And this is where the linear comes into. Namely, if you have one solution of this linear differential equation, and this is true for any linear differential equation, and you have another one, then the sum of them will also be 1. Okay? And for the same reason, if you take a linear equation, you take a constant multiple, that will be again a solution. And, okay, so for those that have taken 2580 linear algebra, what we are saying here that the solutions of a homogeneous second order differential equation actually form a vector space. Namely, the solutions, they're closed under addition and linear combinations. That's exactly what a subspace looks like, a vector space looks like. You have to have linear combinations. So this is called a linear combination. Now, okay, linear might be, you're thinking, linear versus equation. Yeah, but what does linear refer here to? The fact that we have a C1 and a C2 constants here. Like, as if it, right, that's what linear means here. This is a terminology that comes from linear algebra. Again, the word linear is there, where we call this a linear combination. Okay? And this is what happens in general. So, without going too much into the details, which you can read into the book, why and so on, I'm going to just claim the following. So, general solution. So, if we have such a differential equation here, and so it's a, let me write it up again and emphasize here that we are in the homogeneous case. Okay, so suppose, okay, let me make this a new bit more. So we have our linear differential equation, linear second order differential equation. Write it up again, and it's homogeneous. Okay, so let me box it a little bit. This is our linear differential equation. So what does the theory say now? It says there are two solutions, y1 and y2. So if you want, what am I talking about in this particular case here? This was my y1, and this is going to be my y2. So we have two solutions, and called, let's see what they call this. I mean, these kind of terminologies are sometimes a fundamental system of solutions, called a fundamental system of solutions. That sounds very grave, right? Fundamental system of solutions. What does that mean? Means that every other solution every other solution is a linear combination of these. What does a linear combination look like? Well, we said, right, it's C1 times the first one, C2 times the second one. So in other words, the general solution, the general homogeneous solution, because we're talking about homogeneous, right, looks like C1 y1 plus C2 y2. Okay? That's the theory. But as it stands, okay, if you know that this y1 and y2 exist, the first thing is to find them. But the second thing is, what are they? They're solutions. How do I know that there is a fundamental system of equations? I mean, I hope you are convinced there are quite a lot of solutions. There might be even more. And how do I know that this is the fundamental? How do I know that if I give you two solutions, why are these fundamental? So before I even go on, let's give another example here that we will work out later. But I just want to give it now. Where did it go? Okay. So let's look at example. We have the x squared y double prime plus xy prime minus 4y equals 0. Now, first you might complain and say, this is not linear, professor, because that's not how it looks like in linear. But you can make it linear, right? So it is linear if you realize that you can divide everything by x squared. Then we would have, so divide by x squared, right? So let me do this. So I'm going to divide by x squared, and x squared. That will make it really look as a linear one, because then I get this one. And now you see, so that the p of x is here is 1 over x, and the qx is minus 4x squared. So it is linear, okay? And so I'm claiming y1 is x squared is a solution. Now that's not immediately clear, but you could try to verify this. Let's verify this. I'm going to verify it on this part here. So what is the first derivative? So y1 prime would be 2x, y double prime would be 2, right? So let's plug it in. 2 plus 1 over x times y prime, which is 2x, minus 4 over x squared. Sorry, I forgot my y here. That's why I got over certain stock, right? Times of minus 4x squared times y1 would be x squared, right? So what I'm saying is I'm using these three to plug it in here, and that's what I do here. That's the result of it. And you see now that things cancel, right? Because what this is 2 plus 2 minus 4, that is indeed 0. So x squared is a solution. But I'm claiming there's another one. y2 is, well, you might say 5x squared, professor. And now I figure out how it goes. Yes, but that's not good enough. Here's another one, 1 over x squared. Now I'm going to leave this as an exercise for you to check that this is also the case. This is a solution. So I'm just stating that now. So here we have two solutions and different ones. Different in the sense that you cannot make one into the other by a multiple, right? We know that if we take we have set this, right? If we have a solution and we multiply it, then we get a new solution with a constant. If we multiply it with a constant, you cannot multiply this with x, because that will no longer be a solution, right? But if you multiply it with a constant, it will still be a solution. Again, I'm not giving you the details of that. You can look that up into the textbook. So, all right, so. But no multiple of this, constant multiple of this one will ever give me this. So this is essentially different. And that is what it is, fundamental system of equations are. We need these two solutions to be essentially different. Now, what it means is, so y1 and y2, so no, let me put this here because it's part of this theorem. Moreover, to be a fundamental system, we only need y1 over y2 to be not constant. As long as that quotient is not constant, what this means is that, another way of saying that, if you perhaps not, this is easier to check, but perhaps you understand it better if I say, so, i.e. this means they are not proportional. One is not a constant times the other. Proportional. Because we know that if we take a solution and we multiply with a constant, that's a proportional constant, that's proportional to the original one, that is, it gives me a new solution. But if you divide the two, then I get a constant. So that's not a fundamental system. But here this is clearly, this y1 and y2 are fundamental system. In this case, why? Because x squared divided by 1 over x squared, be careful with dividing, right? We have to say that they're not constant of each other. That's x to the fourth is not constant. Right? Constant would mean there's no x there, but there is an x. Okay. So, that's how this works. So what does this mean then? So, conclusion, any solution to this differential equation, let me call it star here, is of the form. So let's think. Let's recapitulate here what this what I said here. Okay, a lot of words, but words is not mathematics. Mathematics is understanding what is going on behind these words. What are the things that we are doing here? So what we have is we have two solutions, and they are fundamentally different in the sense that if you take they are not, one is not a multiple of the other. In other words, if you take the quotient, it's not a constant. Okay, then this result here guarantees me that any solution of this form. So any solution can be written as a linear combination. So c1 x squared plus c2 1 over x squared. So any solution. So this is the general solution. Y equals this expression is the general solution. Okay, why is that important? Well, suppose now I'm going to make, sometimes do this in the color, right? I'm going to add now something to my problem. I'm going to add, say that I want, let me see, let me take something that is, no. Give me a sec here, let's see whether it doesn't really matter. I'm just going to say, I'm going to put in an initial condition. Should I say initial condition? No, I should say initial conditions, right? Because we know for the second order there has to be 2, and they have to be of the form. Let's put in y0 is equal to, no, I cannot take y0. Why not? Because I'm going to divide by x squared. So that will make it undefined. So this is a case where the solution doesn't exist at every point, and at 0 it doesn't exist. So that would not be a valid initial condition. You would notice right away because when you try to plug it in. So I'm going to do it at 1. y1 is 2, and now remember what's the other one would be the derivative at the same point. It technically doesn't have to be the same point, but I've never seen it not be the same point. So I mean the derivative, okay? Y prime equals 5. I'm just making up these numbers, so probably it's not going to be that pretty. How do we find these now? Okay? Can we find a solution that satisfies the differential equation and the initial condition? So this is, I didn't say this, but I didn't write it down, but what I told you was that this equation here with the initial conditions has a unique solution. Okay? So if we add the two initial conditions, so if we have initial condition y0 is, no, I shouldn't y0, right? First of all, why is this so big? Because we don't know what, so the initial conditions would be y at x0 is k0, and the derivative at that point is k1. So if we add these, then there is a unique solution. Provided that x0 is not one of these problematic points. So that's a kind of thing that I'm kind of, as I said, wave my hand. Okay, so this statement here says I must be able to find C1 and C2. How do we do that? Well, okay, how we do this, we plug this in, right? If x is 1, then y is 2. Okay, 2 equals C1 plus C2. Oh, that was easy. Okay. Professor, I cannot find C1 and C2. There's only one equation. Oh yeah, but you only used one different. You only used one initial condition. That's why we have two, so that you can solve for C1 and C2. Y prime. Y prime. Where is Y prime? Professor, I don't have Y prime. Should I go over in the equation? No, you have Y prime because you have Y. So in order to solve the initial condition problem, we will have to work a little bit, and the step that we have to do here is to take the derivative of our solution. Now remember, C1 and C2 are constant, so this would be 2C1x minus 2C2x to the minus 3. Remember, this is, let me rewrite it in a form that makes it more, first of all, more symmetrical and also more easy to take derivatives. We're taking derivatives now, right? So the power rule says that the exponent come down and subtract one of the exponent. Okay, so now in this one, we're gonna have to put in that if x is 1, then y prime is, well, what would you say, 5? That was not nice. I'm gonna make it 6. I don't know why, but let's make it 6. Feel that it comes out better, but let's see. If I plug that in, so y prime is 6, so then we get 6 is equal to 2c1 minus 2c2, right? Because luckily powers of x is always 1. So that means that if we can divide everything by 3 is c1 minus c2. Okay, and so we have now the second equation. It's still not a good choice, but okay, there will be fractions, but that doesn't matter. But yeah, you have to accept that fractions are part of this course. There's no way that there are no fractions. We will have to deal with fractions all the time. Then, if you think about where does this come from? Well, when we take derivatives or antiderivatives, especially when you take antiderivatives, you take the power rule. The power rule is really creates fractions. That's where all these things come from, for one thing. So we have two equations. So again, if you have seen linear algebra, you know how to do this with matrices and so on, but this is such a simple system. You have seen this in 1275 already, pre-calculus course, that you can do this several methods. You can do the method of substitution or the method of elimination. So let's do the method of elimination here. The method of elimination says that you add a multiple of one equation with a multiple of the other equation, a linear combination of these two equations. That's really what you're doing. And then in the hopes that something cancels. Of course, here it is very simple. I take this equation and add it to this equation. Then I get 5 equals 2 times C1 because the C2's cancel. And so I see that C1 is 5 halves. And now I can plug that in, say, for instance, in here. Or, yeah, then I have 3 plus C2 is C1. So that is 3. Oh, I have C1, sorry. So I solved wrong. Okay. Doesn't matter, but I should, let me use the first one here. So C1 is, no, C2, I have to find C2, right? C2 is 2 minus C1, that is 2 minus 5 halves, that is 4 halves, 4 minus 5 halves, that is minus 1 half. So our solution, and this is the unique solution, is y equals 5 halves x squared minus a half x to the power negative 2. Okay, that's the solution of our initial value problem with this differential equation star here. Okay, so all right. I'm skipping a couple of things that are discussed in the book because I really don't think we should spend too much time on this kind of general stuff yet. Let's do one more example, and I will stop with this part. So yeah, sorry. Today we sorry, in this session, I should have perhaps made it a little bit clear here. This is what I'm going to do in this session, and in the next video I will do the non-homogeneous and say how we deal with that there. Okay, but let's do first the homogeneous here. So an example is the equation. Where is the equation? Sorry. No. Oh, I had it, and where did I do it? Yes, okay. Ah, no. Okay. Okay. Y double prime plus omega square y equals 0. What is omega, professor? Okay, so omega is just a constant, and we'll later see why we write omega and not something else. It will become clear. And let's make it right away an initial condition problem. Y0 is 1 and the derivative at 0 is 3. So we eventually, once we have the techniques to solve these things, we will be able to do this. But I'm going to cheat a little bit. So so this is solutions. I'm going to give you two solutions. Y is cosine omega x and y is sine omega x. So that's omega is kind of an angle type of thing here, right? That's why we're using omega. That's what I'm claiming. Okay, we will verify it. So solutions. How? Come back later. So how did we know this is what the solutions? That is come back later. Okay, so this is something that I'm just giving it to you now. I'm telling you, okay, relax, don't worry, I'm giving you the solutions. So these are two solutions. Well, let's verify. I'm going to do both of them because they're really the same. Let's do the y equals sine x, sine omega x. So how do you verify this? Well, we have to plug this into this equation. So what we need is the double derivative. How do you get the double derivative? You can magically get it. No, you have to first get the first derivative. Okay, that is the derivative of sine is cosine, plug in the inside function, times the derivative of the inside function. Now, x is the variable, omega is the constant. So that's the omega comes outside. What is y double prime? Take the derivative of cosine is minus sine, plug in the inside function, and multiply with the derivative of the inside function omega, but I still had an omega. So I get actually minus omega squared sine omega x. And if I now plug this in here, then, so this is what I'm using, right? So I'm using these two guys, well, sorry, not the first, sorry. The y prime, I'm not using that, so let's not circle that. Y prime, I plug this in here, and y, I plug it in here, sine, sorry, y. So what we get is minus omega squared sine omega x plus omega squared times y, and y was just sine omega x. And we see that this cancels. So yes, in the solution, and you can now almost immediately, you don't have to do the calculations to convince yourself that it works for cosine too, because cosine and sine, they're so similar, right? What happens is just the plus and minus signs a little bit different, but eventually they will come down to the same thing. Okay. So, is this a fundamental system? So I'm giving you the system. So that I'm telling you, this is a system of equations. So in this, when you have homeworks, they will always tell you this is the solution. But, well, or these are solutions, verify it. And secondly, is this fundamental? Is this a fundamental system? Well, the only thing I need to do is one multiple of the other. So the question is if I take sine omega x divided by cosine omega x, is this a constant? But what is this? This is by definition tangent of omega x, and tangent is not a constant. Tangent is a real to God function, right? So no. So this is a fundamental system. So remember, it cannot be a constant. As long as it's not constant, yay, we are there. There are other ways to check, and in the textbook they give this thing that they call the Wronskian, but I don't want to do this now. As we need it later, I will discuss it, but for now, let's not go there. This is very easy to check. Sine omega x over cosine omega x is clearly not constant, so we know. So conclusion: the general solution of this homogeneous equation, this very simple homogeneous equation. By the way, it's very simple in the sense it's what we will call, when we will go over this next time, a constant, with constant coefficients. Remember, we had talked about linear first order equation with constant coefficients, and what that meant was that the p, so let's go back here, that meant in the case of first orders, that means that this p was a constant. What does it mean here? Well, that both p and q are constant. And that's the case, right? In fact, this is not even there in this case. This was omega squared. And still we're talking about homogeneous. Okay. So that's a special case of constant, and we will see how to solve this, and we'll see that this is how the solutions look like. That's where that the comeback later is when we do this talk about constant linear second order equations with constant coefficients. It's always a mouthful, and I always have to think exactly what I'm saying, but okay, I think I said correctly this time. Okay, so general solution, how does it look like? Well, we know it's you take each of these two fundamental solutions and take a linear combination of that. So we have two different coefficients here. Make sure that you write different things. If you don't like C1 and C2, I don't like it that much either, so I'm gonna do it differently. I'm gonna just use something that I find easier to understand, A and B. So A and B are just constants. I've been using A and B when we did partial fractions, so I like to use A and B. So that is our general solution. So now, the initial condition, okay, that means we have to plug in. Now, the initial conditions were, if x is 0, then y was 1, right? And the derivative of y was 3. So y was 1 and y prime was 3. So I have y, and I can plug this in, so I get y, 1 is equal to a times the sine of omega times 0, that's 0, plus, I write it up, plus b times cosine of 0. Of course, sine of 0 is 0, and cosine of 0 is 1, so this is b. Oh, I have b already. But what now? I need y prime. So to do y prime, I need to calculate y prime. Okay, we take derivatives. A is a constant. I'm going to take derivative of this, and the inside function is an omega. So this is where the omega comes from, and the derivative of sine is cosine, right? And plug in the inside function. Same thing happens here, except we're going to get the negative sign because the derivative of cosine is negative sign. Are you following this? If you don't follow it, just make it a single step. Do it for yourself. Pause the video, do it for yourself, and convince yourself this is the same thing. Okay. And now I plug in here. If I plug in, so I plug these two data now in here, right? And I see that 3 is equal to a omega cosine 0 minus b omega sine 0. Be careful. Eh? Sometimes, because the omega seems to such a almost like a weird letter, so it must be a variable. No, it's a constant. Don't plug in 0 there. It's the x is 0. Okay, this is 0 and this is 1, so we get a omega is 3, so we see that a is a is 3 over omega. Okay, so what does that mean? Our solution is y is equal to sine omega x, because b was, a 3 over omega sine omega x, plus b was 1, plus cosine omega x. Notice that I actually took omega here, a general thing. I could have do a specific omega here. Okay. Okay. Okay, I want to leave it here. There's a little bit here and there, little things that I'm not spending too much time on. So this is now the homogeneous one. So how do we find? So in the next video, in the next lecture, I want to also explain how do we find, how do we do what we do when we deal with a non-homogeneous one. And I want to do this first because it's kind of a bit more theoretical. So you see, at this point, we have not seen any ways of solving it. I gave you solutions, and so the only work that you have to do is to verify that it's a solution, and then to solve the initial condition problem. Okay, so that the homework will be just focusing on that.